Hello students, today we are going to start with the Fourier series. This is already explained in the or mm, studied in the signal system, but the Fourier series applications are required for the DSP also. So let us start with the Fourier series. Fourier series or the Fourier name is given in the honor of the Joseph Fourier. He was the mathematician. He initialized the Fourier series Fourier transform their application for the basic heat transform and vibrations. The Fourier series Fourier transform and Fourier law are named in his honor. Fourier series. To represent any periodic signal x of t, the Fourier developed an expression which is called as a Fourier series. In term its infinite sum of sine and cosine terms or as well as exponential. Fourier series uses the orthogonality condition. So this orthogonality condition will be explained in my next presentation. Fourier series representation of continuous time periodic signals. So the periodic signal is nothing but the signal is repeats after the some interval itself after the some interval. Suppose signal is x of t is equal to x of t plus t. So after some interval that same signal will be repeat itself. So t is nothing but the fundamental time period and omega is nothing but the fundamental frequency which is nothing but the 2 pi by t where there are the two periodic signals. One is the sinusoidal signal and second one is the complex exponential. Sinusoidal signal may be the in terms of the sine or cosine. Suppose let us take x of t is equal to cos of omega 0 t and complex exponential term is equal to e raised to j omega 0 t where t is the 2 pi by omega. A set of harmonically related complex exponential can be represented by the phi of t, where phi of t is nothing but e raised to j k omega 0 t, where this omega can be expressed as the interval 2 pi by t from this expression. So the term will be e raised to j k 2 pi by t, where k is equal to 0 plus minus 1 plus minus 2 plus minus 3 up to the n up to the n. Next, all these signals are periodic with the period t. According to orthogonal signal space approximation of function x of t with n, mutually orthogonal function is given as x of t is equal to summation k is equal to minus infinity to the infinity a k e raised to j k omega 0 t, that is equal to summation minus infinity to the infinity a k into k is the integer factor into e raised to j k omega 0 t. AK is the Fourier coefficient or we can call it as a coefficient of approximation. This signal x of t is also periodic with period t. This equation number 2 represents the Fourier series representation of the periodic signal. So x of t is equal to summation minus infinity to infinity a k into e raised to j k omega 0 t is the Fourier series representation of the periodic signal x of t. If in this expression the k is equal to 0 is a constant term, if k is equal to plus minus 1, having the fundamental frequency omega 0 is equal, we can call it as the first harmonics. If k is equal to plus minus 2, having the fundamental frequency 2 omega is called as the second harmonics and so on. And if k is equal to plus minus n, having the fundamental frequency n omega 0 is called as the nth harmonics. So now let us derive the Fourier coefficients, that is AK. We know that x of t is equal to, that is summation k is equal to minus infinity to infinity ak e raised to jk omega 0 t. This is the first expression. If you multiply this term, that is e raised to j minus jn omega 0 t on both sides, so you will get the x of t into e raised to minus j n omega 0 t, which is equal to summation minus to infinity a k e raised to j k omega 0 t into e raised to minus j n omega 0 t. For this derivation, you need the pen and paper. Then and then only you will get the derivation of the coefficient, Fourier coefficients. So in first steps, what we do, that is we multiply the equation number 1 by e raised to minus j n omega 0 t, both sides. So you will get this expression. Now consider the integral on the both sides. So integrate the both sides by period 0 to t. So integration of the 0 to t x of t e raised to j k omega 0 t dt into integration of 0 to t summation minus to infinity a k e raised to j k omega 0 t in, into e raised to minus j n omega 0 t into dt. So that is equal to integration of 0 to t summation of k is equal to minus infinity to infinity a k into e raised to, that is e base is same, so you can add the index into e raised to j k minus n into omega 0 t dt. So that is equal to integration of 0 to t x of t e raised to j k omega 0 t dt, that is equal to summation, take the summation side outside, k is equal to minus infinity to infinity, ak is the constant, so take it outside, integration of 0 to t e raised to j into k minus n omega 0 t dt. So this is your equation number 2. By using the ruler's identity, that is e raised to j theta is equal to cos theta plus j sin theta, so you can use for the expression number 2, that is e raised to j theta. So integration of 0 to t e raised to j k minus n into omega 0 t dt, that is equal to 0 to t cos of k minus n omega 0 t dt plus j integration of 0 to t sin k minus n omega 0 t dt, that is equal to integration of 0 to t e raised to j k minus n omega 0 t dt. It is equal to t for k is equal to n. If you place the k is equal to n, you will get the t period. But if k is not equal to n, so this expression will be the 0. Hence in equation 2, the integral is 0 for all values of k except at k is equal to n. Put k is equal to n in equation 2. So this is the equation 2. You will, if you put the k is equal to n, you will get the integration, and if k is not equal to n, you will get the 0 sign, right? So put the k is equal to n in equation number 2, so you will get the integration of 0 to t x of t into e raised to minus j n omega 0 t dt is equal to a n into t, that is a n is equal to, so a n is equal to this t will get transferred to the left hand side, so 1 by t integration of 0 to t e raised to minus j n omega 0 t dt. So n is equal to k, so k is equal to, that is n is replaced by k, ak is equal to 1 by t integration of 0 to t e raised to minus j k omega 0 t dt. So by replacing the n is equal to k, so ak is equal to 1 by t integration of 0 to t e raised to minus j k omega 0 t dt. Therefore x of t is equal to summation, this is your Fourier series equation, k is equal to minus infinity to infinity a k e raised to j k minus n omega 0 t. So ak is equal to 1 by t 0 to t e raised to minus j k omega 0 t dt. Now the shift to the properties of the Fourier series. Fourier series properties. So first property is the linearity property. If x of t, that is Fourier series coefficient, is function of x of n is, and y is the function of x y of n, then the linearity property is, states that a into x of t plus b into y of t is the a into function of x of n plus b into function of y of n. This is the linearity property which obeys the superposition theorem, and it satisfies the signal or the property we can call it as the linearity property. Next one is the time shifting property. Next one is the time shifting property. X of t is equal to Fourier series coefficient is x, a function of x of n. Then time shifting property states that x of t minus t0, that is shifted with the t0, then coefficient will be e into or e raised to minus j n omega 0 t0 is the function of x of n. Then frequency shifting property. If the x of t Fourier coefficient is a function of x of n, then frequency shifting property states that e into e raised to j n omega 0 t0 into x of t is the function of x of n minus n0. Time reversal property. If x of t is the function of x of n, then the time reversal property is x of minus t is equal to function of x of minus n. Time scaling property. X of t is the Fourier coefficient is x function of x of n, then the time scaling property states that if x of at, that is a is the scaled factor, is the function of f of x of n, time scaling property changes the component from omega 0 to a into omega 0. Differentiation and integration properties. If x of t is the function of x of n, then the differentiation property states that derivative of x of t divided by dt, Fourier series coefficient is j into n omega 0 x of n, function of x of n. And integration property, that is integration of x of t dt, and its function will be f of x of n divided by j n omega 0. So in differentiation property, the function will be multiplied by j into j n omega 0, and in integration property, the function will be divided by j n omega 0. Then multiplication and convolution properties. If x of t is the function of x of n and y of t is the function of y of n, then the multiplication property states that the signal is multiplied, that is x of t into y of t, its Fourier coefficient will become t into x, function of x of n into, that is this asterisk sign is nothing but the convolution property, that is convolution of the Fourier series component, that is function of x of n convolved with the function of y of n. And the convolution property is opposite to the multiplication property. If you convert the both signal, that is x of t convolution with the y of t, then the Fourier series coefficient will be t into x of function of x of n into y, function of y of n. In that is, if the input signal is convolved, then Fourier series component will be, or coefficient will be multiplication. And in multiplication theorem, if the signal is multiplication, its Fourier series coefficient will be convolution. Next, conjugate and conjugate symmetry property. If x of t is the function of x of n, then the conjugate property states that x of into t, that is a conjugate property, is function of x of n, that is asterisk sign is indicated as a complex or conjugate property. Conjugate symmetry property for real valued time signal states that the function of x of n, that is conjugate signal, is nothing but function of minus of x of n. And symmetry property for the imaginary valued time signal states that function of x of n, that is complex function, is equal to minus function of minus x of n. Next, Fourier series type. So trigonometric Fourier series, we can call it as TFS. In TFS, sin n omega 0 t and sin m omega 0 are the orthogonal over the period t0 to t0 plus 2 pi omega 0. Now the Fourier series type, the trigonometric Fourier series TFS, that is sin of n omega 0 t and sin m omega 0 t, are the orthogonal over the period t0 to t0 plus 2 pi omega by omega 0. So sine of omega 0 t and sine of 2 omega 0 2 are forms of an orthogonal set. So this point, orthogonal point, will be explained in my next presentation. And this is not a complete without the sine n omega 0 t, because this cosine set is also orthogonal to the sine set. So to complete this set we must include the both sine and cosine terms. Now complete the orthogonal set contains all cosines and sine terms. So that is sine of n omega 0 t and cos of n omega 0 t, where n is 0, n is equal to 0 1 2. So therefore any function x of t in the interval t0 to t0 plus 2 pi by omega 0 can be represented as x of t is equal to a0 cos of omega 0 t plus a1 cos of cos of omega 0 t plus a2 cos 2 omega 0 t up to an cos of n omega 0 t plus b1 sin omega 0 t plus b1 1 first, that is b1 sin omega 0 t plus up to b2 sin omega 2 2 omega t up to bn n sin omega 0 t. So therefore that is equal to a0 plus a1 cos 1 first omega 0 t plus a2 cos of 2 omega t up to an cos of n omega t. There, that is plus b1 sin 1 omega t b2 sin 2 omega t up to the bn sin n omega t. So therefore x of t is equal to a0 plus summation of n is equal to 1 to n infinity an cos of n omega 0 t plus bn n omega 0 t for t is from the t0 to t0 plus t. The above expression or equation represents the trigonometric Fourier representation of the x of t, where a0 is equal to 1 by t 1 by t integration of t0 to t0 plus t0 plus t x of t d2 dt. So an is equal to, so x of t is equal to a0 plus summation n is equal to 1 to infinity a1 an cos of n omega 0 t plus bn sin of n omega 0 t for period t is less than t0 plus t but greater than t0. And this expression is called the TFS, that is trigonometric Fourier series representation of the x of t, where a0 and an can be derived, that is an is equal to integration x of t cos of n omega 0 t divided by integration of cos square n omega 0 t, and bn is integration of x of t sin n omega 0 t dt divided by integration of sin square n omega 0 t dt. Here integration of 0 to t0 to t0 plus t cos square n omega 0 t dt is equal to integration of 0 to t0 to t0 plus t sin square n omega 0 t dt is equal to t by 2. So therefore an is equal to 2 by t integration of t0 to t0 plus t x of t cos of n omega 0 t dt, and bn is equal to 2 by t integration of t0 to t0 plus t x of t sin of n omega 0 t dt. That is the next x series is the first series was the trigonometric Fourier series. The second series is the exponential Fourier series EFS. For the complex exponential function e raised to j n omega 0 t, where n is equal to 0 plus minus 1 plus minus 2, which is the orthogonal over the period t0 to t0 plus t, where t is the fundamental period t is equal to 2 pi by omega 0, and this complete set so is possible to represent any function as shown below. So f of t is equal to first Fourier series coefficient plus first f1 plus f2 plus f3 into multiplied by exponential complex exponential function, and plus 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 reverse reverse f1 e raised to minus j plus f2 reverse function of Fourier series f2 e raised to minus j2 omega 0 to up to fn. So the Fourier function f of t is equal to summation n is equal to 0 to n is equal to minus infinity to infinity fn e raised to minus j n omega 0 t. So this is the positive coefficient of functions and these are the negative coefficients of function. And so function f of t is equal to summation n is equal to minus infinity to infinity f of n or any signal x of t into e raised to j n omega 0 t for the period t0 to t0 plus t. The equation 1 represents the exponential Fourier series representation signal of f of t over the period t0 to t0 plus t, and the Fourier coefficient is given as a f of n is equal to integration over the period f of t into e raised to j n omega 0 t. This asterisk sign is the complex conjugate into dt divided by in e raised to integration over the period e raised to j n omega 0 t dt into e raised to j n omega 0 t dt. So after the solving this, you will get the function 1 by t integration over the period t0 to t0 plus t f of t into e raised to minus j n omega 0 t dt. So Fourier transform, the main drawback of Fourier series, it is only applicable to the periodic signals. There are some naturally signals produced such as a non-periodic or aperiodic signal, which cannot be represented by using the Fourier series. So this is the main drawback of the Fourier series, that Fourier series is only applicable for the periodic signal, but some signals are the natural signals or aperiodic signals, and that cannot be represented by using the Fourier series. And to overcome this short drawback, the Fourier developed the mathematical model to transform the signals between the time or spatial domain to the frequency domain and vice versa, and which is called as a Fourier transform. And Fourier transform has many applications in physics and engineering as analysis of LTI, that is linear time invariant system, radar, astronomy and signal processing. So driving the Fourier transform from the Fourier series, so we know that the consider the periodic signal f of t with the period t, and the complex Fourier representation of f of t is equal to summation k is equal to minus t infinity to the infinity ak into e raised to j k omega 0 t. This is the expression for the Fourier series, that is equal to k is equal to minus infinity to the infinity a k into e raised to j. Omega can be represented by 2 pi by t0 k into t, where 1 by t0 is the delta of f, that is equation 1 becomes f of t is equal to summation of k is equal to minus infinity to the infinity a k into e raised to j2 pi k delta ft. And you know the ak equation, ak is equal to 1 by t0 integration over the period f of t e raised to minus j k omega 0 t dt. Substituting in the equation number 2, so you will get f of t is equal to integration of minus k is equal to minus integration infinity to the infinity 1 by t integration over the period f of t into e raised to minus j k omega 0 t dt into e raised to minus j2 pi k delta f of t. Let t is equal to t by 2. So your summation will become, or the right hand side becomes, in summation of k is equal to minus infinity to the infinity integration over the period minus t by 2 to the t by 2 f of t into e raised to minus j2 pi k into delta f of t dt into e raised to j2 pi k delta ft into delta f. So t tends to the infinity, delta f approaches to the differential, continuous becomes a continuous variable f, and the summation becomes the integration. that is f of t limit t tends to infinity, summation of k is equal to minus infinity to infinity, integration over the period f of t into e raised to minus j 2 pi k delta f of t into e raised to j 2 pi k delta f t into delta f, that is equal to the integration of f of t into e raised to minus j 2 pi f t dt into e raised to minus j 2 pi f t df, that is f is equal to integration minus infinity to the infinity f of omega into e raised to minus j omega t omega, where f of omega is the integration of minus infinity to the infinity f of t into e raised to minus j 2 pi f t dt. That is Fourier transform signal is f of t is equal to f of omega, which is nothing but the integration of minus infinity to infinity f of t e raised to minus j omega t dt. And if you take the inverse, the Fourier transform f of t is equal to integration of minus infinity to infinity f of omega into e raised to minus j omega t d omega. So these are the two transform signal. F of t is the uh, can be transformed to Fourier signal, and Fourier transform original signal can be recovered back by the taking the integration inverse of the Fourier transform. Next, the some representation of the basic signal Fourier transform. So this is the get signal, that is Fourier transform of get function having the period having the maximum amplitude a and period is minus t by t to the t by 2. So its Fourier transform becomes f of omega is equal to a t sa omega t divided by 2. Next, impulse function, the Fourier transform of impulse function is 1. Unit step function, the Fourier transform of unit step function is pi of delta omega plus 1 by j omega. Exponential, so as per the exponential signal, that is exponentially increasing, decreasing, e raised to minus omega, so you will get this kind of the Fourier series. Minus e raised to minus at, so Fourier transform is 1 by a plus j omega. E raised to minus at u of t, so the signal plus u of t, so the signal 1 by a plus omega. E raised to minus at modulus of t, so 2 pi by a square plus omega square. E raised to minus j omega 0 t, its Fourier transform becomes delta of minus omega 0 t. Signal function, so its Fourier transform becomes the 2 pi by omega. The next one is the condition for the existence of Fourier transform. Any function f of t can be represented by using Fourier transform only when the function satisfies the Dirichlet conditions. That is, f of t has the finite number of maximum and minima, and the next is finite number of discontinuities in the signal f of t in the given interval of time only, and it must be the absolutely integral in the interval of time, that is integration of minus infinity to infinity modulus of f of t dt is less than infinity. So this is the existence of the Fourier transform. Thank you.